So now we are in part 5. Okay, so there's no summary in here. Good. But I see. Okay, I see. That's what I'm saying, right? So we've got pluses here, and here we've got minuses. Okay, so that was not far away from. Um, but we have information stored in a toric code, which is a grid of noisy qubits. The only way the bad things can happen is if a load of bits of bit flips happen. If bad things also happen, the qubits get measured. Clearly, we have no way of detecting or correcting these, so they will build up over time and soon mess up our logical qubits. Okay, how can we manage them? We have a rule for each white square. Each must have an even number of ones around it. By looking at which of these rules are broken, we can work out how to get rid of the bit flip errors. But let's forget about these rules for a while. Instead, we will come up with some new rules that can be used to detect measurements. Rules for blue plaquettes. Let's now think about the code using the plus and minus states from last time. With this, we can declare a rule for each blue squares when looked at it in terms of pluses and minuses. Each must have an even number of minuses and therefore an even number of pluses. There are many possible patterns of pluses and minuses that obey these rules. Here are a few. Yeah. Not here. Or the blue one, sorry. Yeah. This should look pretty familiar. They're the same ones as before, but with 0 replaced with pluses and 1 to minus, with squares with blue and everything turned 90 degrees. Now we go off and get a cup of tea, and the gremlin sees an opportunity for some mischief. It measures one of the qubits to see if it's 0 or 1. Every qubit here is plus or minus, both of which are superposition of zeros and ones. So the measured qubit will randomly choose one or the other. Let's say for the sake of argument, it chooses 0. When we get back from our tea break, we can check whether the blue squares are following the rules. Most are, but okay. But what about the two near the measured qubit? Yeah. When we measure those squares, we're asking them to look at how many of the qubits are in state plus and minus, and tell us whether the minus is odd or even for most of the qubits, which are simply in state plus or minus. This is an easy job. But the measured one is in state 0, superposition of plus and minus. This has to decide whether to be plus or minus before the question can be answered. If it decides to be plus, then it is which is what this qubit was originally. The rules are obeyed in these squares. The qubit has also been forced into a state that is nothing like the 0 state in ground measure. All is well. If it decides to be the opposite of what it was originally, the effect is similar to a bit flip, except this kind of flip turns plus into minus and minus into plus. We can call these phase flips. Yeah, actually. So this is okay. So yeah, of course, it's obvious. Well, it's not. Yeah, I think I'll have to assume it's obvious so far. Because I keep having that problem with the Bloch sphere where the Z rotations at the face, but it doesn't necessarily still a face of 180 degrees. I get it that it doesn't matter what the global phase is. And yeah, that's a rotation. That's like between the minus and the plus, there is 180 degrees. So there is like the phase. The phase split causes the rules to be broken into two blue squares. But just like with bit flips, and this allows us to detect and correct the errors. Also, the qubit is again forced into a state that has nothing to do with one of the Gremlin measured states, which is again out of date. With these rules protecting the code, correct the errors. Okay, yeah. With these rules, protecting the code from measurements is exactly the same as protecting it from bit flips. So if a few measurements here and there won't cause a big problem, we can just detect them, remove their effects, and update the state to make sure their results can tell anyone anything about our logical qubit. Yeah, the thing is, it kind of makes sense because if you're just putting zeros and ones, then you don't care whether they get measured because that's what they are. If you put them into pluses or minuses, then you do care what you measure. And the trick is if you see a zero, it means that from the perspective of a plus and minus, so the x-axis, when you try to measure that, then you're gonna get a random result. If for the case where there's an error, which is in this case a one. Just detect that more effect. The only way, yeah, exactly. Combining the rules, we now have a set of rules for dealing with b-flips and a set of for dealing with phase flips. Yeah, but we really need them to work together so we can deal with both at the same time. Getting things to work together in quantum mechanics is not always possible. So suppose we have a single qubit and set the two rules. We measure either 0, 1 and some 0, 0. The only way to make a qubit always give us the result 0 for a 0, 1 measurement, as rule I requires, is to have it in state 0, but that is a superposition of 0 and plus, so it gives the result half the time when we do a plus minus measurement, breaking rule 2. Similarly, the plus state is the only one that always obeys the rule 2, but it breaks the rule I half the time. So if the same was true for the rules, the squares would get lots of broken rules all the time. So impossible to get enough to take correct errors because all the random nonsense that comes from the rules fighting each other. Okay. But there is a big difference between rules I and II and the rules we use in the Doric code. There is no just one big state that satisfies the rules for the white squares, but there are many patterns of zeros and ones that do it. I don't know what I'm reading, give me a second. But there is a big difference between rules. There's not just one state that satisfies the rules for the white squares, but there are many patterns of zeros and ones that do it. And any superposition of these will obey them too. There are also many patterns of pluses and minuses that obey the blue square rules, as do their superpositions with more possibilities. There is hope. Any state can be thought of either in terms of zeros and ones or in terms of pluses and minuses, just like a single qubit in states. There can be thought of, yeah, it could be a superposition. What about trickier superpositions? So, I mean, what this is basically telling us is, so, no, yeah, there's not size. It's not just so nice. Just like single qubit says it. Say some superposition of blue. Okay. There are also many patterns that are available. Both sets of, so they're just simple patterns. We need a big superposition to make sure that the rules can work well together. In fact, for a logical zero, we need a superposition of every possible set of zeros and ones that could be used for a logical zero. which is a lot in this case. Making such a complicated set of correlated qubits is going to be quite hard. That's why you can't buy toric code from the shops. With both sets of rules working well together, we just need to keep checking on both types of squares. So when we see white rules broken, we know that the bit flip has happened, and when we see blue rules broken, we detect the correct phase flips as long as unlikely things don't happen. Yeah, but you cannot have. Can you have both? Can you have both things? What is the meaning of having both types of qubit states mixed in one grid if I have zeros, ones, pluses, and minuses? Because so it kind of can still be, but it becomes complicated how to map that grid to any possible qubit state. That just doesn't seem like a reasonable direction to me so far. So far, we assume that the only kind of bad things that can happen are B flips and unwanted measurements using ones. But what about phase flips or unwanted measurements of pluses and minuses? Yay! Our code naturally sorts these out too. What about those other crazy weird quantum stuff? It turns out that anything that could ever happen can be thought of as some combination of beat and phase flips. So whatever happens, once we measure that rule, the rules are being obeyed. The noise gets forced to decide what kind of beat and phase flip it wants to be. Then we detect and correct those, and all is well. The toric code. Okay. So high level makes sense. Well, perhaps it doesn't protect from everything. Big and horrible errors can still happen. Blah blah blah. A long time. Our logical qubit will last a long time, and if they are not rare enough, we just make our code bigger, so they need to be ever bigger and more horrible before they can mess this up. So that's the toric code in 5 parts. Next, we'll move on to its flat brother, the planar code. But first, in this pause, we take a look at some of the maths behind all this. I try to keep it with as little maths as possible, but it did turn out to be a bit long. There's a little bit of teleportation in there, though. Okay, let me just check it out quickly. Fun measurements for pairs of qubits. Unis, what is this? Committing measurements. I think I'm not gonna go through all that. Fun. Okay, so that's this one here. So is it the next part then? The planar code. So that was the toric code because of the toric geometric figure, but the planar code is what we want to get to. I mean, that's what I read somewhere, is that that someone figured out the planar code works as well, and it's a simpler model for that. But it's still, that doesn't answer. The toric code doesn't. This introduction to the toric code didn't answer how do you perform operations in this. How do you negate? How do you do a set rotation? How do you do all this kind of stuff? And how do you represent a state of a qubit that is neither a 0 or 1 nor plus or minus? So maybe the planar code is easier, and then that kind of then makes sense. Let's see. But this is from 2016 though. Maybe I should find some more recent. I mean, I don't know how much more has happened in 3 years since the research for this. But so what is the next one? I just want to know what is the next one. Next one, flat brother, the planar code. Is this the entanglement with with the simplest math possible? It doesn't look like. No, that's not it. I'm just trying to find it before I switch. Okay, maybe I'll just do this out of the video. So, a couple of little things. Grammar correction, the puzzle. See if see if I find this next part. Okay. Cool. That's it so far.